Here we go. Let's get started on the mole and the molar conversions. These are going to be examples from your notes for those of you who are wanting some extra examples. So before we actually start, let's recall a few things. We're going to be needing molar mass, which is the flipped lesson we did before where we add everything up on the periodic table for our formulas. And remember, it's going to have units of grams per mole. And then we're also going to be needing to use Avogadro's number. And we will only be using Avogadro's number when we see words like how many molecules, or if they start with molecules or atoms. We will not be using it every single time. And that is a big mistake that a lot of students make. They think, oh, I see this problem, I've got to use Avogadro's number, and they get it wrong because you only need to use it at specific times. So we're going to say atoms, or it could be molecules per mole, okay? It will be atoms whenever you're talking about an element, and it'll be molecules whenever you're talking about a compound. And remember, it's always per 1 mole, and we need to make sure we remember that. Always just put 1 with the mole. The number is going to either go with the atoms or the molecules, or it's going to go with the grams. So let's get started on our first example. Okay, here we see we have how many grams of sodium chloride are in 5.00 moles of NaCl. So we're going to always start with what we are given, and we want to go to grams, okay? So we see grams and we see moles, we know we're going to need a molar mass. And so we'll abbreviate that. The molar mass of sodium, if you add them up, is 22.99 plus 35.45 for chlorine, and we get 58.44 grams per mole. If you don't remember how to do that, pause the video and go look up the molar mass of sodium and chloride and add them together, and you should get that same answer. So here we go with 5.00 moles of sodium chloride. We draw our grid. We know we want to get rid of moles of sodium chloride, so it immediately goes on the bottom. Okay? And we are wanting to go to grams of sodium chloride, so we put it on the top. It's always per 1 mole. And that means the 58.44 goes on the top. We cancel and cancel. We have 2 numbers on the top. So that means we're going to multiply. And when we multiply that, we get 292.22. But we are not done with that because we need to put it in the proper significant figures, which if we go look at this is 3 significant figures. So we would say 1, 2, 3. This, we would check what comes behind it, does not round up. So our final answer would be 292 grams of sodium chloride, and that would be our final answer. All right, let's do this next one. Now, basically what I'm doing in this PowerPoint is I'm doing one of each kind of calculation so you have an example to follow. In this case, this time we want to go moles to grams. So it's asking us how many moles, so that's what we're going to be looking for, are in 210 grams of lead oxide. Now that 2 is supposed to be little, but for some reason on this PowerPoint it makes them big. So just going to have to deal with that. So we're going to start with what they gave us, 210 grams, and that point means that that 0 is significant because they're saying it's exactly that much. So PbO2, draw our grid. We know that we want to get rid of grams, so we're going to put it on the bottom, and we're going to go to 1 mole on the top. So at this point, we need to get a molar mass of lead oxide, and we can jot that down up here. Lead is 207.2, and then plus the oxygen, and we have 2 of those, so we need to do 2 times 16, and when we do that, we should get that it is 239.2 grams per mole. So now we'll plug that into our problem. So the 239.2 goes on the bottom, and now we have a number on the top, a number on the bottom, so that means we need to divide. So we would take 210 divided by the 239.2, and when we do that, we should get 0.878 moles of lead oxide. Technically that is lead 4 oxide, but we don't know about that yet. And so that just made sure everything canceled. because of that decimal, that made us have 3 significant figures, so that is why we put our answer as 0.878. All right, here we go with some Avogadro number calculation. And like I told you, here's one of our clues. The word atoms is in there. So that means we're going to need to do the 6.02 times 10 to the 23rd somewhere in that problem. Now, depending on whether we are going to atoms or from atoms will depend on whether we need to multiply or divide by that number. So we're going to start with what they gave us, which was 4.25 moles. So we jot that down. And that is just of lead by itself. So we're going to do our grid. We want to get rid of moles, so it goes on the bottom. Remember what we've been saying, it's always per 1 mole. So the Avogadro's number is going to go on top. 6.02 times 10 to the 23rd atoms of lead. So what that's saying is for every 1 mole of lead, there are that many atoms. Okay, and we've talked about that. It's a really, really big number. So now we have both numbers on the top, so we need to multiply. We go and see that we have 3 significant figures right here. So we need our answer to be in significant figures. So what I want to do is I'm going to write this down exactly how I would type it, because sometimes we forget about how to type in the times 10. So on your calculator, it should look like this: 4.25 times 6.02 second, EE button, 23. And then you would hit enter. Okay, and when you do that, you should get that answer is 2.28 times 10 to the 24th atoms of lead. Okay, so now let's do one where we're starting with atoms instead of moles. So this time we're going to be going to moles. So we're going to start with the 8.24 times 10 to the 24th atoms, and this time it's sodium. Okay, we have atoms of sodium, so we know we want to get rid of atoms of sodium, and that means we're going to go to 1 mole of sodium on the top. So now our Avogadro's number comes down here. Okay, I have a number on the top, a number on the bottom, so this time it means I need to divide. So remember to type in the second E when you want to put those exponents in. And when you get finished doing that, your atoms of sodium will be canceling, and we will be left with 13.7 moles of sodium. And that would be our answer. 3 significant figures here and 3 in our answer, so we have that correct. All right, let's do some two-step conversions. And this time we're going from atoms, or they want to know how many atoms in 3.99 grams. So there is no possible way that we can go straight from grams to atoms. So when you see a problem like this that has atoms in grams or molecules in grams, you're going to have to go through the mole. So, and that will always be the middle step in our problem. So we're going to have to go through the mole. So we're going to start with our 3.99 grams because we always start with what they gave us. So 3.99 grams of potassium. Okay, I need to get rid of grams, and the only way I can do that is using my molar mass. So I've got grams per 1 mole of potassium. We look at our periodic table, and we see that it's 39.10 grams of potassium in 1 mole of potassium. So now my grams of potassium are canceling out, and now I need to use Avogadro's number because I want to get rid of moles and because I'm ultimately trying to go to atoms. So I would say 1 mole of potassium, and in every 1 mole of potassium, there are 6.02 times 10 to the 23rd atoms. Okay, and so now I have, excuse me, I have numbers on the top and on the bottom. So I'm going to need to multiply and divide. So I will multiply the top numbers and then divide by the bottom numbers. And this would be a very good time for you to pause it and put it in your calculator and then see if you get the same answer that I do. So when we record our answer, we want to make sure we put it in 3 significant figures because of that right there. Remember, we never let our conversion factors dictate our significant figures. It's always the measured number. And so after we put that in our calculator, I come up with, and hopefully you do too, 6.14 times 10 to the 22 atoms of potassium. How'd you do? Hopefully you got that right. Here we go, last problem for today. This time we're going the other direction. This time we're looking for grams, and we're starting with atoms of helium. So we want to start with that number right there, which is 3.03 times 10 to the 21 atoms of helium. And so because we're starting with atoms of helium, we want to put atoms of helium on the bottom. So it's going to be 1 mole of helium, and then of course our Avogadro's number, 6.02 times 10 to the 23rd atoms of helium. And so now we've gotten rid of helium in the atom form, and so now we can go from moles to grams, because remember the moles are always going to be the middle step in these type of problems. So we have 1 mole of helium on the bottom. We look up the molar mass of helium from our periodic table, and we see that it is 4.0 grams of helium per 1 mole. Again, I have numbers on the top, numbers on the bottom. So I'm going to need to multiply the numbers on the top, divide by the numbers on the bottom. And again, good time to pause your video, type it in your calculator, and see if you get the same answer as me. And if you do, which I hope that you are able to do that, you should get 0.0201 grams of helium. And again, checking that our significant figures match. This has 3 and this has 3, so we are good to go. All right, here's your joke. What do you call a fish with 2 sodium atoms? You call him a tuna. Ha ha, get it? A tuna. Now that is sodium funny.